Welcome to this UniLogic tutorial. UniLogic is the complete application development environment for our Unitronics UniStream control platform.
Hello, my name is Shane Pratt and I'm an applications engineer at Unitronics. This tutorial is about how to implement proportional, integral, and derivative or PID control into your application. Based off of a system feedback, a PID loop will continuously control a dynamic process where variables are constantly changing. The purpose of this control is to maintain a desired set point based on feedback. This is a standalone process, meaning you can set it and forget it, and the system will regulate itself. Some examples of where systems use PID are in heating and cooling applications, such as regulating the temperature in a room, ventilation systems, such as regulating incoming and outgoing airflow, motion control, such as maintaining the speed of a motor, chemical process control, such as controlling levels of enzymes in a mixture, and many other processes. It is possible to use the simple on-off control principle to maintain the desired output. However, this type of control results in oscillations of the system. The PID process allows to minimize overshoot of the system and damp out any resulting oscillations, running the system as efficiently as possible. PID control will keep a process running as close as possible to a desired set point based on the feedback from the system. This feedback is known as the process value and is sampled according to a specified time interval. Once the controller understands what state the system is in comparison with the set point, it will adjust the output accordingly to either get to that set point or maintain the set point based on the error value. This is performed through three calculations: proportional action, integral action, and derivative action. The sum of these three actions will be the output of your PID control, or the control value, and is continually changed based on the feedback. The three actions that make up the control value are implemented once the system enters a defined proportional band. The proportional band creates a high and low limit around the set point for the PID process, and this is defined as a percentage of the input system range. Therefore, the proportional range will be from the set point minus X% of the system range to the set point plus X% of the system range, where X is defined as the percentage of the input range for the proportional band. In a heating process, when the process value is below the proportional band, the output generated will be at 100%, or driving the system as fast as possible to the set point. Once it is in the proportional band, PID is then implemented to adjust the output according to the error between the set point and the process value. Let's break the actions down to their individual control. Proportional control will adjust the output of the system proportionally to how far it is from the set point. For instance, when the process value is 75% away from the set point, the proportional action will be at 75%. When the process value is 50% away from the set point, the proportional action will be at 50%, and so on. Proportional control is a direct response to the system based on the error, or the difference between the set point and the process value. However, too small of a proportional band will create an overshoot and oscillations around the set point, and too large of a proportional band will not allow an efficient response to the system, or riding right below the set point. Integral control will adjust not only the magnitude of the error and drive the system to the set point faster, but also the duration of the error. The action is calculated by summing the previous errors over a given time interval and producing an output from this sum. In turn, the integral accumulative action can recognize how the system has reacted previously and reduce the current error. In other words, it will allow the system to settle around the set point faster and reduce the error. Derivative control is implemented to reduce overshoot and oscillations to improve the stability of the system. The action is calculated by the rate of change of the error and produces an output from this calculation. It slows the response of the control value, but results in damping out any oscillations that may occur from the proportional and integral control and compensates for overshoot from these controls. In other words, it will smooth the output. In UniLogic, there are two types of PID structs for creating a PID loop: PID config and PID AT params. The PID config struct will be the working struct to configure the PID loop and used to run the PID process. However, this struct will not be retained, so upon power loss, all of the parameters will be cleared. The PID AT param struct is a retained struct. This is where the PID parameters are stored to and loaded from via the PID config struct when a PID process is being used. It is also important to note that using the non-retained memory is faster than using the retained memory. Therefore, the non-retained PID config struct is used to run the PID loop. Within the PID config struct, parameters needed to be configured for the set point, sample time, input high and low limits, output high and low limits, and the action forward or reversed. Also, associate the process value to an input or feedback, and link the control value to the output of the process. This defines the span of the system, where the system needs to be, and how often to poll where the system is currently. If the system is not going to be using auto-tune parameters, a proportional band, integral time, and derivative time will need to be defined for the process to run. Since every system is different, in order to calculate the best values for any given PID controlled system with the UniStream, an auto-tune process can be ran. An auto-tune process in UniLogic will run the system through 1 to 3 cycles, ramping the output fully on at 100% until the process value reaches the set point, then letting the momentum of the system carry the process value over the set point and back down again. Upon falling back onto the set point, the system then pushes the output to 100% until it reaches the set point again. These are known as auto-tune cycles or stages. Once the auto-tune cycles are complete, the proper values for each parameter are calculated based on the information the auto-tune cycles have collected. This tutorial will cover implementing a PID process with auto-tuned parameters. Upon the auto-tune completion, save the auto-tune calculated PID parameters to the retained PID AT param struct and run your PID process when the application requires it. Also, before running the PID Auto-tune, it is recommended to run a reset PID Auto-tune to clear the configuration struct of any unwanted previous parameters. In this tutorial, a PID process will control the height of a floating ping pong ball in a tube. The process value will be a signal from an ultrasonic sensor to report the height of the ball, and the control value will be a signal to control the speed of a fan. The process will be considered a heating PID process because we will need to move the ball up to the set point from its ambient state. Now, to begin creating the project. First, set up the input point for the process value and the output point for the control value. Navigating to the Solution Explorer and under the Hardware Configuration tab, choose the Local I/O option. The I/O modules were set up beforehand for simplification of this tutorial. For this project, the input will be monitored via a 0 to 10 volt DC analog signal, so a UIA 0402N has been added to the project from the toolbox on the right-hand side. The control value will be manipulating a PWM high-speed output. A UID 0808 THS module has been added to the project for this purpose. Also, create 2 PID structs for the application. One for configuring the PID parameters and one for saving the PID parameters. In the Global Tags list, click the Add New Tag button in the upper left-hand corner of the window. Choose the type to be PID config and name the struct PID configuration. Click Add at the bottom of the tag editor and create another tag with the type as PID AT params. Name the struct saved PID run params and save. Take a look at the PID configuration struct. Here are the parameters covered earlier in the slideshow. A sample time, input high and low limit, output high and low limit, An action to perform will be needed to be entered. The process value will need to be linked to the input or feedback of the system, or the 0 to 10 volt DC input signal. And the control value will need to be linked to the output of the control system, or the PWM output. In the HMI portion of this example, a few screens have been prepared in advance. First, the main PID screen. This is a screen that is shown upon first power up and is where the set point, frequency for the output, a run for the auto-tune process, and a run for the PID loop can be entered. In addition, there are numeric boxes to view the current values for the process value, control value, the status of the PID loop, the action of the PID process, and the individual P, I, and D parameters. On the right-hand side of the screen, find the linear gauge for screen monitoring of the set point compared to the feedback of the overall system range. Finally, there are two buttons at the bottom of the screen: the Edit PID Parameters button to navigate to the PID Parameters page for us to edit, and the PID Graph button to view the PID values on a trend graph over time. The Edit PID Parameters screen should be viewed and edited before running either of the PID processes. This is where one can set or ensure the proper process value high and low limits, control value high and low limits, sample time, and action. If any of these values are changed, this data must be loaded in order for us to store it into the struct for running the PID process. Notice on the right side of the screen, manually tuned P, I, and D parameters may be entered to run the PID process instead of the auto-tune. The third screen prepared is the PID graph, where the PID loop can be monitored over a period of time. Below the trend graph, there is a legend for the colors of the curves that will be displayed on the graph. Viewing this graph can be helpful when troubleshooting any discrepancies in the PID loop by monitoring how the PID parameters are reacting in the PID process. Navigating to the data sampler, notice 6 values are sampled for the trend graph: the set point, process value, control value, and the independent P, I, and D values. Next, the values must be stored into the PID struct. In the latter, first store the analog input to the process value. In net 1, place a store function block against the main rail of the main routine, so the most current value of the analog input will be placed into the process value. Choose the analog input for the A parameter, navigate through the UIA 0402N struct, the inputs, and input 0 was used. For the B parameter, navigate through the PID config struct and choose the process value. Once the set point, system limits, and process value have been set, the PID process can be started. First, perform an auto-tune to calculate the best P, I, and D values for the process. Upon the positive transition of the Run Auto-tune button, reset the PID Auto-tune data via the function block under the PID tab in the toolbox. This will clear out any unwanted parameters and the PID config struct that may have been left over from a previous process. Link the configuration struct here in the A parameter. In the following net, run the PID Auto-tune off of a direct contact for the Run Auto-tune bit. This function block will perform the auto-tune process. Parameter A is looking for the PID struct to use, so link the PID config struct created earlier. Parameter B is looking for the amount of cycles to run for the auto-tune process: 1, 2, or 3 cycles. The most precise PID values are calculated by running 3 cycles. Once the auto-tune process is complete and the PID values are calculated, it is good practice to save the values to a retained struct. It is also helpful in the event of a power loss. The PID system will load the same PID values when started back up. Or, when obtaining PID values for multiple set points on the same system, the retained struct can help. Trigger this off of a positive transition contact of the auto-tune done bit found in the PID config struct. Then, from under the PID tab in the toolbox, Connect the saved PID Auto-tune data in series with the positive transition contact. In the A parameter, link the PID config struct used to run the Auto-tune function block. And in the B parameter, link the retained PID AT param struct created earlier. This will store the PID information needed to be ran for the PID loop from our configuration struct into the retained struct. At the end of this run, connect the reset coil for the run Auto-tune bit. Next, run the PID loop when the run PID button is pressed. Add a direct contact for the run PID bit in the following net, and then in series, add the run PID function block from under the PID tab. The A parameter is asking for the PID struct to run this function block, so use the PID config struct created earlier. This will use the PID config struct parameters to run the PID process for the system. If the unit was turned off or if power was lost, the parameters must be reloaded into the PID config struct. This is where the PID AT param struct comes into play. In this project, upon startup, the retained PID parameters will be loaded to the PID config struct to run the PID loop. The parameters may also be loaded through a button pushed on the PID edit parameter screen. In the next available net, place a direct contact against the main rail. Link this to the general system struct and choose the ladder initial cycle bit. In series, from under the PID tab in the toolbox, add the load PID Auto-tune data function block. Scroll over the A parameter and notice this is looking for the PID run param struct. Link the PID run param struct here. The B parameter is looking for the PID config struct to place the data into. Link the PID config struct we created for running the Auto-tune process. Since the parameters could also be loaded via a button push on the PID edit parameter screen, place a positive transition contact in parallel with the ladder initial cycle bit, and link this to the load Auto-tune data bit, and connect the contact to the load PID Auto-tune data function block. A net will also be added for the event of a setpoint change. To ensure that the new setpoint is retained in the event of a power loss, store this new value into the PID run param struct. So upon the positive transition of the setpoint entry bit, use a store function block to store the PID config.setPoint into the PID run param.setPoint. This way, the current parameters of the PID process will always be retained. Now that the ladder for the PID loop has been created, the output of the loop must be linked to something. For this application, a high-speed output will control a solid-state relay. The frequency will be set to a constant number, but the duty cycle will be manipulated to run the end device, in this case a fan, with more or less power. Since the output should only be running while the PID process is running, in the net below, add a direct contact and link this contact to the run PID bit. In parallel with this contact, add another direct contact for the run Auto-tune bit. Then, in series with these contacts, add a store function block to store the PID config.control value to the duty cycle of the PWM high-speed output module by choosing the UID 0808 THS1 and then selecting B1 PWM duty cycle channel 1. Although the control value is stored to the duty cycle of the PWM output, the output has not yet been triggered to run. So in series with the store function block, place a direct coil and link this to the UID 0808 THS1 module and choose the PWM enable bit. Now, the PWM output will run with the instructed duty cycle during the run PID and run Auto-tune process. Another thing to add to this run is the instruction to start and end the sampling for our trend graph. In series with the direct coil for the PWM enable bit, place another direct coil and link this to the data sampler 1 start/end sampling. Now the PID parameters will be graphed while the processes are running. With the application now complete, download the application to the UniStream. I have connected to the PLC using a VNC viewer to show how the screen and system is reacting according to the functions created in the ladder. First, notice the set point and frequency boxes are highlighted in red. These require user entry in order for the PID process to run. The span of this system is from 150 millimeters to 1600 millimeters, as shown by the linear gauge on the right side of the screen. Choose the set point to be 1020 millimeters. Once entered, the set point is changed on the linear gauge to the right and is shown where it has changed to in accordance with the rest of the system. Next, enter a frequency for the high-speed output to run at. Enter 1 million millihertz or 1 kilohertz. The rest of the boxes on the screen are not highlighted since these are read-only parameters to view while the system is running. To ensure the rest of the PID parameters are set correctly, press the Edit PID Param button to navigate to the Edit PID Parameters page. As of now, all the parameters are showing a value of 0. This is because these boxes are linked to the retained PID struct, which has no information loaded into them. Enter the data so that in the event of a power loss, the system will recover the parameters we wanted. The PV low limit is 150 millimeters. The PV high limit is 1600 millimeters. The CV low limit will be 200, which is 20.0% duty cycle. This is due to the system we are running. The process value acts too aggressively to a 0% duty cycle or being completely shut off. Therefore, we have manipulated the system to only be able to drop to 20% duty cycle for a less abrupt drop in the process value. The CV high limit is 800, which is 80.0%. This was also manipulated because the system also responds very abruptly to 100% duty cycle or fully on. An 80% high limit for the control value will allow the process to rise less abruptly for a more smooth PID process. A value of 10 is usually recommended for the sample time, which is 100 milliseconds. So every 100 milliseconds, the PID system will pull the feedback or process value and recalculate the control value to drive the process value to the set point. The action will be heating or starting from the lowest system point and driving the process value to the set point, rather than starting from the highest system point and cooling down to the set point. After any of these parameters are changed, press the Load Auto-tune Data button to transfer the PID parameters to the PID config struct that will be used to run the PID process. On the right-hand side of the screen, manually tuned parameters may be entered for PID loops configured by oneself or to fine-tune values calculated by the auto-tune. Once an auto-tune process has been completed, the proportional, integral, and derivative values may be displayed here, as well as the main PID screen. However, users may only edit the parameters here. The third screen in this program, PID Graph, displays the values of the PID process on a trend over time. As explained before, this allows for easy comprehension of how their values are relating to each other over time and is very handy in the PID troubleshooting process. Displayed below the graph is a legend for what the colors are referencing. Press the back button and we will return to the main PID screen. This tutorial covers running a PID process with auto-tune parameters, so press the Run Auto-tune button to begin the auto-tune process. Upon pressing this button, the Run PID button becomes hidden and the system ramps the output at its maximum drive 80% 4 times. Remember, the first cycle is the initialization cycle. Once the auto-tune cycle is completed, the Run PID button appears again and the P, I, and D parameters are displayed on the left. Now that the parameters have been calculated for the system, the PID loop can be ran. Pressing the Run PID bit, we can see the process value reacting to the control value on our linear gauge to the right. Also, notice the right arrow indicating the set point, or where the process value should be. For a more precise record of where the process value is currently, along with how much we are outputting to the control value, view the numeric boxes under where the frequency is set. Head to the PID graph screen and monitor the values in real time. This concludes our tutorial on implementing PID into your UniLogic application. You can find more information and example applications on our website. Thank you.